So now I'd like to expand a little bit on this concept of forces. A very important skill in physics is free body diagrams. And what free body diagrams are is a diagram where you're able to show all the forces acting on a specific object, on a specific thing, particle, person, whatever it is. Um, and they're pretty easy to draw. It's not very difficult, so we're going to do it using the same example here. The units here are not, the units and numbers are not as important since this is all kind of relative. But it is still, it's slightly important because of magnitudes of things, but I'll get to that in a second. So the way any free body diagram works is you have your center, your object, your whatever you're dealing with here, which you just draw as a dot usually. And connected to the dots are all the arrows that show the forces, right? So since forces are vectors because acceleration is a vector, you want to, they have direction, and so you want to draw that with the arrows. And the size of the arrows are the magnitude, meaning call it the strength of that force, how large the force is. So 50 newtons is larger than 10 newtons. That's just, 50 is larger than 10. And so you would represent that by the size of the arrow. So again, it's all very relative. So on this box, you have a couple of different forces acting on it. First of all, we have the one that we already highlighted, right? We did the problem, the last video, and we said that this guy's pushing this box with a force of 50 newtons. So that's one of the forces. So we're going to draw 50 newtons is quite a bit. So we're going to draw, I can't draw an arrow. 50 newtons here. We're just going to call that force sub P. I'm just going to say force of push. It doesn't matter exactly what we label it, as long as it's a force. And that force is, I don't think that line is straight, but it's, as we see here, it's entirely horizontal. This guy's pushing it directly to the right, his right, as we see by this arrow over here. Second, and there's three forces acting here, with a couple of assumptions, but we're going to assume that this is a frictionless surface, this ground over here, which means there's no resistance, no force pushing back from the guy pushing, because we want to make this a little simpler. And so therefore there's two other forces. One of them we experience every day. It's a very basic force. I mean, if you don't know what I'm talking about already, it's gravity, right? So gravity in itself, when you say gravity, that's really just an acceleration, which is that number that we hear all the time, the 9.8 meters per second squared. That's the acceleration of gravity. If we want to say the force of gravity, that's just a mass times that 9.8 meters per second squared. But usually when drawing free body diagrams, we're not including numbers. We could, but it's really not that useful. So we just make this 9.8 equal to g. So this becomes mg. And so that's how we're going to write it, mg. And since it's going to be, we don't really know what the mass of the guy, we do know the mass of the box. It says right here, 5 kilograms. So 5 kilograms times 9.8, let me draw my units, 9.8 meters per second squared is, I don't know, grab your calculators. Oh, I think it should be, no, I'm not going to try to do it in my head because I'll get something wrong. But 9.8 times 5 is 49 newtons. And that's slightly less than 50. So we should draw that arrow. Let me redraw it. We should redraw it, or draw it if you didn't in the first place, to be slightly, very slightly less than that, the arrow of the force pushed by the guy. So I think that's about it. The other force, the last one's a little less obvious, but it's called the normal force. And what that is the force that the ground is exerting on the box. And the basic idea is, if there's gravity pulling down, why isn't the object going down? I mean, that's kind of an obvious thing to say because there's a ground there. But that means that there has to be a force acting up from that ground, and that's exactly what normal force is. Uh, the equation for normal force is, well, there's not one equation, but the essential idea is that it's a force perpendicular to the ground. So if the box was tilted on the ground, the force would be this way. So it's just opposite in a way to the ground. In this case, since the ground is flat, it's just directly up, and it's going to be the exact opposite of the force of gravity because the box isn't moving up or down. So it has to be equivalent. So it just kind of cancels out, literally does cancel out. And so a normal force, we could write N, or you could do F sub N. Different people do it different ways, but this is going to be equal to mg. Just if you want to think in vectors, it's going to be negative mg, or mg is negative, so it's just going to be positive, negative mg, which is positive, right? But we usually just say mg, we just say n when we're drawing free body diagrams. This is more when you're setting up an equation. And so this is the basic free body diagram, assuming that this is a frictionless surface of this box being pushed by this